So I believe we're recording now. So again, welcome to the fourth and final session of the IGARS 2020 online summer school, remote sensing of volcanoes. And our grand finale here with what we've all been waiting for, the large buildup. Rob Wright from Hawaii Institute of Geophysics and Planetology, University of Hawaii at Manoa, will be speaking to us about thermal remote sensing of volcanoes, background and principles. So we'll do this as we've been doing the other ones. If you have questions that come up along the way, please write them in the chat, and then I can try to convey those to Rob at the appropriate time. And I believe he's got 3 different sections, and so there might be short breaks in between and dedicated time for questions as well. But I'll turn it over to Rob, and thank you so much.
Okay, can you hear me fine, Ryan? Is that still good?
Yes, can hear you just fine.
Okay, so hello everybody. Sorry we can't meet in person. Maybe we will at a future conference or meeting. So yeah, so today I know you've had some information from Fabrizia on thermal remote sensing with specific examples related to Italy, and a bit more work on hyperspectral remote sensing. So I'm going to give 3 presentations. The first one is background and principles. The second will be topics related to the use of high spatial resolution data. And then the third one will be topics related to the use of low spatial resolution data. In the talk, the slides will be made available to you along with the other slides that you've seen. I'm going to aim this at the level of somebody who knows a little bit about remote sensing. So if you're a subject matter expert, then you can tell me where I've got it wrong. But I'm going to try and aim to help people who are trying to get into this from the ground up. So that's why we're going to start with some background and principles first. So I am... Okay. So first of all, this covers some of the stuff that you've been going over the whole thing, but we're using, this is a remote sensing workshop. So we're interested in what we can measure about a volcano without actually being on the ground. So what do volcanoes do that we can measure from space? So there are a few things while a volcano is in a state of unrest. So on the left-hand side, can you see my mouse, Ryan, when I move it around, my cursor?
Sorry, yes, I can.
Yeah, okay. So when the volcano is in a state of unrest, what might they be doing that we can measure? Well, there might be a crater lake at the summit. So this is the lake at Poas. We could measure the color of this lake water, or we could measure its temperature. So that's a low temperature thermal remote sensing example. There might be a hydrothermal system or a geothermal anomaly which intensifies as magma rises at shallow depths beneath the volcano. Again, we could measure that. That would be a low temperature geothermal type anomaly. I'm not going to cover this, but we can use thermal remote sensing to measure these gases, particular sulfur dioxide, or if you're having very high resolution data, water and carbon dioxide. You spoke about deformation with Scott, I think, yesterday. Seismicity, unfortunately, we can't do from space. So before an eruption begins, we can look at this kind of stuff, some of which we can approach using thermal remote sensing. During an eruption, well, we can measure the presence of lava at the surface. So we have lava domes, which tend to be relatively small and relatively low temperature. Mafic lava flows and lava lakes, which tend to be small or large, relatively small, but the radiating temperatures are really rather high. Ash clouds, and then also volcanic gas. Again, the main methods for quantifying presence, absence, and concentration of ash use long-wave infrared remote sensing. Sulfur dioxide, the typical Vince Real-Muto type retrieval uses the long wave. We're not going to cover those, but the kind of data that some of the data we'll be talking about today could be used for both of those things. So there are several things that we want to know about volcanoes that we can measure from space, and some of those are quite specific to the realm of thermal remote sensing. So just a bit of a background to thermal remote sensing and then thermal remote sensing volcanoes. So this chart just shows a few things. Obviously, when we're looking at the Earth's surface, we have to look in an atmospheric window or we don't see anything. So typically we do remote sensing in the visible, the near infrared, the shortwave infrared, the middle infrared, and then also the long wave infrared out here. So the wavelength is down here on a log scale. So most remote sensing is confined to one of two realms. So I've got radiance, irradiance here, which is energy striking a target, and then excitance here, which is energy leaving a target. A lot of the time we look in the reflected part of the spectrum. So this green curve is the top of the atmosphere solar irradiance. So this is just the energy of the sun. So I've put the equations for all of this stuff that I've used to produce all the graphs here, so you can recreate them yourselves in Excel or IDL or whatever. So typically when we're looking at reflected light, we look in the visible and the shortwave and the near infrared part of the spectrum. Most thermal infrared takes place out here in the long wave part of the spectrum, maybe into the middle infrared, because most ambient temperature targets on the Earth's surface radiate most of their energy at these wavelengths, these long wave infrared wavelengths. I've just shown here the excitance from a 600K black body. So this is something radiating at 300 degrees C roughly, which is the kind of temperature we might expect from a days old lava flow surface. So you can see that when we look at thermal remote sensing of volcanoes, we're not just constrained to the long wave infrared part of the spectrum. We can actually utilize the mid-wave part of the spectrum, so the 3 to 5 micron region, and also the short-wave infrared part of the spectrum, which typically extends from about 1.2 to 2.5 microns. At the resolutions we measure from space, this isn't true for Ryan's drone data, but things are rarely hot enough to radiate in the visible part of the spectrum when we're looking at resolutions of 30 meters a kilometer, typical Earth remote sensing sensors. So, sorry, I'll go back. So much of what we want to do with remote sensing is based on, for thermal remote sensing, is based on accurately quantifying the amount of radiance here, excitance, which leaves the surface, so that we can either, and if we do that really precisely, we can do a few things. We can compare the intensity of an eruption at the same volcano through time. We can compare the intensity of activity at one volcano with another in space. But if we know the radiance, as I'm going to show, we can also work out other things like the temperature of the surface. And if we can work out the temperature, we can get into other variables, for example, cooling rate, maybe even viscosity. But the first thing is accurately working out surface leaving radiance, how much radiance leaves the target. In order to accurately work that out, we need to know something about the emitting capability of the material, which is its emissivity. And we also need to know something about how much energy the atmosphere absorbs as it travels from the surface to the sensor, and also how much energy at thermal wavelengths, how much energy the atmosphere actually emits. The latter is contaminant. The absorption is something that we need to quantify if we want to actually get back to a parameter called surface leaving radiance. So this first session is going to be all about those topics. So an introduction to remote sensing, and then an introduction to the topics of thermal remote sensing, which impinge on our ability to accurately work out the radiance leaving an active lava flow and or its temperature. So just for those who don't know much about remote sensing, this is just an overview of the remote sensing process. So I'm going to skip to the next slide. This is for the reflected case. So given that we're dealing mostly with thermal emission, I'm going to skip to this one. So if you look on the lower part of this figure, there's an active lava flow. So we might want to know something about this. We might want to know its temperature. We might want to know its cooling rate. We might want to extend and use those variables to work out other things like the effusion rate. So those are the condition of the surface, right? Now, what we end up with is on the right-hand side here, we end up with a satellite image where in each pixel we have a DN value. Now, we're going to assume that the condition we're interested in measuring, for example, temperature, is a function, the DN is a function of that condition. So how is that true? Well, the only thing we measure from this lava flow in space is the light, radiation, electromagnetic radiation, or in remote sensing parlance, the spectral radiance, denoted usually as L, which leaves that surface. That's the thing we actually measure. Okay. So the lava flow emits radiance. We have a sensor which samples the radiance coming from the Earth's surface. Now, typically, this might be a whisk broom scanner or a push broom scanner or a whisk push scanner. But anyway, the way it works is the spacecraft travels forward in its path at about 7 kilometers a second. It looks down, and then it uses optics, either a refractive optic, so lenses, or more commonly a reflective optic, to sample the amount of energy which comes from the Earth's surface. Okay, so it just builds up a checkerboard, scanning left to right, or just push brooming some detector array which is projected onto the ground, and it samples the amount of light from each area on the surface. So we define that as the IFOV, the instantaneous field of view, but typically people just refer to it as the pixel size of the data. Okay. So for Landsat TM, each of those gray boxes would be a 30 by 30 meter patch of ground, which the spacecraft samples in a period of time. So white light, or all wavelengths, come up from the target. They pass through some kind of focusing mechanism. We're interested in spectral radiance, so the amount of energy at each wavelength. We're not interested in white light. We want to split it up and look at the thermal infrared or the midwave infrared. So we do that using some kind of spectrograph. So this is not a prism, could be a diffraction grating, could be filters, might be an interferometric technique. Fabrizio probably spoke about diffraction gratings yesterday, I guess. But anyway, we split the light into its different components or frequencies or wavelengths or colors. And then we have some kind of transducer which converts an incident flux of photons into a stream of photoelectrons in a circuit that looks kind of like this. So photoelectrons strike the conductor, the semiconductor. Electrons are boosted from the conduction band, this band, into the conduction band, and in the presence of a bias voltage, so we just have a bias voltage here which runs some electrons through this circuit, the extra electrons are swept up as they pass around here as this thing is scanning backwards and forwards, and we can measure that stream of photoelectrons as either a change in current across, through, or a voltage drop across a reference resistor. So we convert a stream of photons into a stream of photoelectrons, which we then can change into convert into a voltage change over time, where the sampling in the system allows us to map a voltage to a pixel. So that's these spots here. That's an analog representation. We then convert that to a digital representation, so a digital number. People are familiar with these things. And then we transmit that down to the Earth, and that's what you get when you look at a remote sensing data set in ENVI or ER Mapper or whatever it is you're using, where we have a digital number in each of the channels that the spectrograph split the light into. And basically what we're going to assume is the dn is a function of condition, and we assume that because the dn is a function of the change in voltage. The change in voltage is a function of the change in measured radiance, and the change in radiance is a function of the temperature, as I'll show, and the temperature is related to the condition, maybe cooling rate, that we're ultimately interested in trying to measure. So a key part in all this is calibration, which is in this area here. So sensors have to be well calibrated. If you can calibrate a sensor well, or if it's very stable over time, then you can always relate the physical output of the instrument, which is a change in voltage, to the amount of light which struck the, which arrived at the pupil plane, which is the thing, the ultimate thing that we're interested in measuring. So how do you measure the temperature of something without touching it? So a couple of equations here. These are Planck's blackbody radiation equations. So spectral radiant excitance, m lambda. So I put all the constants in here and the units. The one on the top shows you how to work out spectral radiant excitance if you have wavelength in meters and temperature in Kelvin. Gives you an output in watts per meter squared per meter, and all of the all of the constants are in here. A more common version to use is this one on the bottom part here, where we roll a bunch of these constants up into what people call the first and second radiation constants. This is quite a common one because it gives the output in watts per meter squared per micron. And what input wavelength in micron, temperature in Kelvin, and these are the values of the constants. Now, if you just plot in Excel wavelength versus temperature using this equation, you will produce these curves, okay, for various values of temperature and wavelength. So these are very similar to the curves I showed on the first slide, so you can do this yourself. It's pretty easy. Basically, it just shows you that if I make a measurement of radiant excitance at a particular wavelength, I can invert that to a measurement of the temperature of the emitting surface. That's how we measure the temperature of something remotely without touching it. It's really quite simple. Planck's blackbody law specifically relates to spectral radiant excitance, and I've just drawn a cartoon about that here. That's basically all of the energy in watts, so joules per second, per meter squared, per micron, so per wavelength interval or per band. It's the amount of energy radiating into an entire hemisphere. We don't measure that in remote sensing. We usually calibrate that to L lambda, which is in watts per meter squared per steradian per micron, which just is a directionality term, if you like, to represent the fact that we don't measure the whole hemisphere. The spacecraft is usually at one point in the sky, and we make a measurement through a solid angle, not overall solid angles. So anyway, it's that simple. The only thing that varies in here is temperature and wavelength. And if we know the wavelength at which the spacecraft made the measurement of radiance, we can take a measurement of radiance and back out the temperature. So the temperatures we back out, usually in the remote sensing literature, you'll see people make reference to things like brightness temperatures and radiation temperatures. The important thing is they're not kinetic temperatures. So the kinetic temperature is the thing we really want to know. That's the temperature you would measure if you actually physically touch the thing you're trying to take the temperature of. So that's, you know, proportional to the average kinetic energy of the molecules and things that make up the thing that we're measuring. And the hotter something is, the more violently the molecules vibrate and clash against each other. So the internal kinetic energy is proportional to temperature. Planck's blackbody radiation law, again shown here, basically is great because it shows us that we can actually work out what that temperature is from a measurement of radiance at a particular wavelength. But it's not a kinetic temperature. Quite often, what we measure from a satellite data is we will make a measurement of radiance at one wavelength. So this might be band 32 of MODIS. We'll get a single measurement of radiance at a single wavelength. And if we can use Planck's law, so this equation is just this solves for T. If we do that at a single wavelength, so wavelength here, radiance measurement here, we'll get a value of 300 Kelvin for the temperature. If we make that measurement of radiance at one wavelength, then we will have measured what people call a brightness temperature. So a temperature that's derived from a measurement of radiance at a single wavelength is called a brightness temperature. If we integrate lots of measurements over many wavelengths, we get what people call a radiation temperature. There's also things like a color temperature, which astronomers use, but we don't use that in remote sensing. What you'll encounter most is this thing called a brightness temperature, because usually we take a single measurement of radiance in a single band and convert it to a temperature. The important thing is that's not a kinetic temperature. Okay, and I'll explain why that is as we go along. What we have to do is, if we want to accurately work out the radiance leaving a lava flow and then work out its cooling rate, we need to convert our brightness temperature to a radiation temperature. So that's basically the process of doing that is what's going to cover the next several slides. So the first thing we have to do is work out how good the surface is at emitting light. So people have heard of black bodies, I presume. So a black body is something which radiates the maximum amount of energy possible at each wavelength given its temperature. It's a perfectly efficient radiator. So I plotted a curve up here. This is a blackbody curve for a target at 300 Kelvin. So if you used, and I've changed the value actually, spectral radiance. So just keep track of units in remote sensing. This will all become clear later. But if I use Planck's blackbody radiation law, as I'll show you in a couple of slides, slightly modified by a factor of pi, and I plug in at each wavelength a temperature of 300 K, I'll get this black curve, right, which is a Planck curve. Okay. So this black curve represents the perfect ideal, the maximum amount any surface, regardless of its composition, can emit if its temperature is 300 K at each of these wavelengths is shown by this black curve. Okay, nothing can emit more energy at this temperature. It's the ideal. If we take a lump of silicon dioxide, this is a lump of big quartz crystal that we have lined up, that we use a lot in the lab for some of our instruments, and we heat it to 300 K, and then we point an instrument at it, we'll measure the red curve. Okay, so this is a black body at 300 K, and the red curve is silicon dioxide at 300 K. So you'll see the black body. So here's a black body in our lab. So if I set this to 300 K and pointed my instrument at this surface, I'd measure the black curve. If I then spin the instrument around instantly and point it at this quartz crystal, I'll measure the red curve. So a few things you can see. At these wavelengths, this lump of quartz, it emits as efficiently as a black body. And it emits as efficiently as a black body here, and nearly as efficiently as a black body here, okay? But at these wavelengths, it's much less efficient. So at 9 microns, this lump of quartz emits half the energy it could if it was a perfect radiator. Does everybody see that, presumably? Okay, so the problem with this is if I make a measurement of, if I fly over a lump of quartz with the spacecraft and I make a measurement at 7.5, somebody's drawing on my screen. Thanks. And if I make a measurement of spectral radiance at 7.5 microns, which would be kind of hard because the atmosphere absorbs that, and I plugged 8 microns into the Planck blackbody relationship and then used a value of 7.5 microns, I would get an accurate temperature for that lump of quartz. I get a temperature of 300 Kelvin, right? But if I took a measurement of quartz emission at 9 microns, I get a value of 3.2 watts per meter squared per steradian per micron. If I plug that into the Planck equation, I'm not going to get a temperature of 300 K. Okay, I'm going to get a bad temperature. My brightness temperature will not be the true kinetic temperature of the quartz. Okay? Because at these wavelengths, the quartz is much less efficient at radiating energy. Okay? And it's less efficient because of its chemical composition and structure. So different materials absorb and emit light at different frequencies or wavelengths with different efficiencies. In the quantum world, this will be because of the distance that all the electrons that form the ions and then the bonds that connect the ions reside with respect to the nucleus, which allows photons of different wavelengths of light to be preferentially absorbed or not absorbed. At these wavelengths that you see these large emission deficiencies, basically it's telling me that the silicon dioxide is very efficient at absorbing energy or light at this wavelength. If it's very efficient at absorbing light, that means it isn't very efficient at radiating light, which is why I have an emission deficiency at these wavelengths. Now, emissivity is the parameter which describes the efficiency of something to emit. And this is something we need to know in remote sensing if we're going to try and convert a brightness temperature to a kinetic temperature. We have to correct for this non-perfect emission from the thing we're studying. So we go to the literature, or we go to ENVI, or we go to the ASTA Spectral library, which is held at JPL, and we just pluck out an emissivity for the composition of the surface that we're interested in studying. The way we generate these, most simply, we use a piece of equipment slightly more complicated than this, but we make a measurement of a black body at 300 Kelvin. We make a measurement of our target material at the same temperature. We divide one by the other, and that's what I get on the bottom half here, where I have emissivity, which is unitless between 0 and 1. At these wavelengths, quartz approximates the behavior of a black body. At these wavelengths, it does not. But I have this emissivity factor. So if I make a measurement of the radiance emitted by a ground target at 9 microns, I know that if I want to convert that brightness temperature to a kinetic temperature, I have to correct the result by a factor of 0.33, because otherwise my brightness temperature will be really wrong. If I know the emissivity, I can do that correction. So just as an example, here are a few more things. Everything has its own capability to emit, or emissivity, which is based on its chemistry and to a certain extent physical structure. There are, so I've computed these here and plotted them up. Emissivity is the radiance from the thing you're interested in studying on the top line here to the radiance emitted by a black body at the same temperature. You divide one by the other, and you get these emissivity curves. So that's just what I've illustrated here. So it's this that you need to go from brightness temperature to a kinetic temperature. Just to reiterate, if I was in space and I was making these measurements of radiance, what I would measure would be the red curve if the peridotite was at 300 K. And I use peridotite and granite here. The emissivities for basalt and rhyolite, their volcanic equivalents are very, very similar. What I measure would be the red curve. What Planck's black body radiation law would tell me would be I would be expecting to see the black curve, okay, because it's by definition the black body radiation law. If I know the emissivity, I can convert one to the other and get a more accurate temperature, convert my brightness temperature to a kinetic temperature, which is what I care about. So just looping back a little bit, Planck's law is basically hemispherical excitance, or the amount of energy radiated over an entire hemisphere. So m lambda in these units is everything that comes from the source in a narrow wavelength channel over the whole hemisphere. In remote sensing, we look from one direction. So this is a better example or replication of the remote sensing case. With Landsat and everything else, if you convert dn to the physical SI quantity that we care about, you end up converting it to spectral radiance, typically in units of watts per meter squared per steradian per micron, although the calibration coefficients vary instrument to instrument. So old Landsat calibrations, if you went to the literature, they would be in milliwatts per centimeter squared per steradian per centimeter, I think. So when you're doing this kind of work, you've always got to be careful. You invariably often you have to multiply or divide by factors of 10 to make sure that you don't get it wrong. But it's quite simple to work out. again, I've rewritten this here so that it's in watts per meter squared per micron. Now, excitance is the energy that comes over the whole hemisphere. What we measure in remote sensing is spectral radiance, and m lambda is related to L lambda simply by dividing by pi. So people call this magic pi in the radiometric literature. It's that simple, okay? So you can do this in various places. Sometimes people put a pi in here. Sometimes people divide one of the radiation constants by pi, which changes its value. But anyway, if you have m lambda, you convert it to L lambda by dividing by pi. L lambda is what we measure in remote sensing. And the reason it's the unit of remote sensing is that it's range invariant. It doesn't matter how far or close away you are to the ground target, spectral radiance doesn't change, whereas excitance does change. So for example, you'll see here watts per meter squared per micron. So m lambda decreases. There's like an inverse square law. As we move from the source, it spreads out over the area that it passes through. So spectral radiance changes depending on how far away or close you are to the target. Okay. Spectral radiance does not, because radiance is the total energy passing through each one of these surfaces, which doesn't change at all. Okay, so that's why we use spectral radiance. And I've just plotted up here some curves, again, using this relationship that we've seen before. The difference between the black curve and the red curve is just a factor of pi at each wavelength. Okay, so the moral of this story is when you're doing this kind of work, check your units. You know, work out whether you're in spectral excitance space or spectral radiance space. Easy to convert one to the other, just divide or multiply by pi. Check your units, make sure you're not a factor of 10 too large or too small, and you'll be able to work out temperatures from remotely sensed data. So the first thing you have to do is convert the dN to spectral radiance. So for example, with Landsat thematic mapper, the way I would do this is in NV, I go into this pixel and I go in Landsat band 5, which is 2.2 microns, and I get a dN of 205. I plug 205 in here, take these calibration coefficients, which you can get from the website or a paper somewhere. These are all easily found. Plug it into this equation. The result I get is 24.8 watts per meter squared per steradian per micron. So I could take this value from that dN, plug it into that equation, and work out the temperature of the ground within this pixel. Okay, so quite easy. These calibration coefficients, they're basically just the equation of a straight line. I mean, if you make an instrument that doesn't have that kind of calibration, you're going to have a tough time. Most instruments are linear. If they're not, then that's either a special detector or there's something weird going on. But you can find these online. Sometimes they're in the header file of the data. Other time you can go to the literature and just pull up the pre-launch calibrations. So as I said, to convert a brightness temperature to a radiance temperature, a kinetic temperature, the first thing we have to do is know the emissivity, which is the capability of a surface to emit, which is dependent on its chemistry, its chemical composition, and its physical structure. If we do that, then we can convert part of the way to work out, to convert our brightness temperature to a kinetic temperature. This works fine on Mars and the Moon. Okay, so that's all you have to do. If you're looking at the surface temperature of Mars, that's pretty much all you have to do. If you're looking at the surface temperature of the Moon, that is all you have to do because it has no atmosphere. On Earth, the energy which leaves the surface, so let's call it surface leaving radiance, that's what we care about. And if we've corrected for the emissivity, we now have a precise estimate of the surface leaving radiance. What we don't know yet is how much of that survives the journey from the ground to the spacecraft. So this is at satellite radiance or at sensor radiance, or some people refer to it as pupil plane irradiance because it's the energy striking the target. But anyway, in the thermally emitted case, this is the reflected case, which we're not going to talk about that much. But in the thermally emitted case, the thing we're interested in studying, so this is a pixel down here, it has a certain temperature, it emits a certain amount of light. If we know the emissivity of that surface, we can correct the amount it does emit to the amount it would emit were it a black body, which is good. We need to do that. So the energy leaves the surface, but unfortunately, the atmosphere absorbs some of that energy before it reaches the sensor. If we don't correct for that energy, we will back out a bad temperature, right? Some photons will be lost, so we need to correct for those. Some photons will also be added. You know, if we're in the thermal infrared part of the spectrum, so 8 to 12, 8 to 14 microns, the atmosphere emits energy of its own. It emits energy down and it emits energy up. So the energy the atmosphere emits up to the sensor measures. The energy that the atmosphere emits down and is then reflected from the surface, the sensor also measures. And it doesn't know the difference between the photons that are emitted by the atmosphere, which we don't care about, the photons which are emitted down from the atmosphere and reflect from the surface, which we don't care about either, and the photons which are emitted from the ground, which we do care about, because the photons that are emitted from the ground are proportional in each wavelength to the spectral radiance, which I've just shown you is how we're going to back out the temperature of this thing. So to work out an accurate kinetic temperature from a brightness temperature, an at-satellite radiance measurement, we have to know the emissivity. We also have to correct for the effects of the atmosphere. So typically we'd use, typically people use ModTran. So I've just shown a few ModTran plots here. Basically what ModTran does is it takes, you kind of tell it what altitude your volcano is at. Is it at sea level? Is it Kilauea? Or is it in the Andes? Is it Lascaux? You then build a model atmosphere, which basically describes the capability of the atmosphere to emit and absorb radiation at the wavelength that you care about. You then set a ground surface temperature, and you then say, well, okay, if the ground surface temperature is 300 Kelvin and it's at 5,000 meters, how many photons does the ground radiate? And then it just divides the atmosphere into plane parallel layers, and ModTran just passes those photons from layer to layer and says, well, how many got absorbed in the first layer and how many were added? So how many got absorbed and how many were added by this term in the first layer, and it works out how many photons arrive at the bottom of the second layer. And then it just repeats that up through 100 kilometers. At the end of this, you can work out, and this is an example here, the transmissivity of the atmosphere. And you can also get this term, which is F, which is the emission of the atmosphere into the field of view. And basically all you do is you say, well, so to work out to take your at-satellite radiance measurement and convert it to a measurement of surface temperature, you calibrate it using this. You go to the literature and you say, well, if my measurement of radiance is at 11 microns, I'm going to get the emissivity of, sorry, I'm skipping around. You're going to get the emissivity of basalt at 11 microns, and it's going to be 0.85 or something. And then you're going to say, well, okay, so now I know the radiance and I know the emissivity of basalt. Now, how much light did the atmosphere add and subtract from the signal? And you're going to go here and you're going to read across, and you're going to say, well, the atmosphere the atmosphere stole 10% of my signal. You know, these are unitless values between 0 and 1. And if you know those three things, then you can work out an accurate kinetic temperature from a remotely sensed radiance measurement. So just an example, this is a Landsat image. So I would zoom in. There are some lava flows in these pixels. I would take this pixel and I would find the DN. I would use the calibration coefficients I've just shown you, and I would convert that to spectral radiance. I know this is basalt, so I would go to the spectral library and I would get my emissivity, and I would say, well, the emissivity is about 0.9. That would be this value here. I would then run ModTran and I'd say, well, at this wavelength, the transmission of the atmosphere is about 0.9. So I would plug 0.9 in here. And if I do that, I've taken a measurement of that satellite radiance, and I've corrected that measurement of radiance for transmissivity and emissivity. If I plug that measurement of radiance into the inverted Planck equation, it's still a brightness temperature, right? But it will be very close to the true kinetic temperature of the surface, which is what we want. Now, if you don't care about working out the temperature, you just want a precise measurement of radiance, then you still need to work out variations in the atmosphere and emissivity of the target, okay? So whether you're doing radiance or temperature, the first step is to correct for the transmission of the atmosphere and the emissivity of the surface. So I'll describe in the next session, so we'll have plenty of time for questions. If you're studying water bodies, or if you're studying the temperature of clouds, or if you're studying the temperature of a patch of vegetation, then that's pretty much all you need to do. Basically, the thing you care about is homogeneous at the scale of the pixel, or it fills the pixel. And at the scale of the pixel, it has the same temperature. So we call these targets thermally homogeneous. So you can imagine this, right? If you took a Landsat image of the middle of the Pacific Ocean, and the TIERS data at the moment have a spatial resolution of 100 meters. The surface temperature of the ocean really doesn't change on a scale of 100 meters, right? So if you use what I've just shown you, I mean, you'll get a skin temperature, so you'll have to correct for that, but you'll get a pretty accurate measurement of the surface temperature. The problem with the remote sensing of volcanoes is that this temperature inversion process gets complicated because the target is usually thermally complex. That is, we have something really hot and something relatively cool, both mixed together in a single pixel. Okay, and also it may not fill the instantaneous field of view of the sensor. So, you know, these are two complicating factors. We'll talk about more about these in the next couple of slides, in the next couple of sessions. But all of these curves here can be produced with, they can be produced with the equations that I've either shown you or I'm going to show you. So it's really simple to produce these things. But just to show you some examples, I can't actually remember all of these curves, so I've put it on the next slide so that both you and I can make sense of this later. But let's look at surfaces curves 1 through 4. So those are 4 thermally homogeneous surfaces radiating at temperatures of -50, -5, 15, and 20. So one might be a cloud. These might be land surfaces at night and by day, okay? So if I take -50 degrees C, convert it to Kelvin, plug it into the equations I just showed you, I'll get this black curve, which tells me how much energy that surface will radiate at each of these wavelengths. And you can see these are unimodal curves, right? It's a single temperature, it's a single curve, it's unimodal. Now I can invert this curve at any wavelength. I can make a measurement of radiance at a particular wavelength and invert that to get back to the temperature -50 degrees C. And it doesn't matter which wavelength I make the measurement of radiance at, I'll still get back to -50 degrees C. Okay. Once I add a small amount of hot stuff, so let's look at curve, where am I? Let's look at curve, well, let's look at curve 5. Okay, so that's the red curve. So curve 5 is exactly the same as, what am I doing? Curve 1, 2, 3, 4. Oh, 5. So curve 5 is a lava flow which fills the field of view with crust at 600 K and cracks in the flow interior, which are at 1400 K, and the cracks occupy 1%, 1/100% of the flow surface. Okay, so that's the red curve. So this is a huge, if this is in MODIS data, this is a huge lava flow. This is something at a kilometer square at 600 K with tiny cracks radiating at the eruption temperature. And you can see that basically this thing emits a huge amount of energy. So this is the background, curve 4. Okay, so this might be an adjacent pixel. This is the pixel containing the lava flow. And I think you can see it would be really easy for me to distinguish the lava flow pixel from the ambient ground surrounding the lava at any of these wavelengths, right? Because the target pixel, the lava pixel, just radiates orders of magnitude more radiance at every single wavelength that we look at here. Okay, really easy to detect this pixel in a data set. It would, if I inverted the Planck function using a measurement of radiance at a certain wavelength, it would also give me not too inaccurate temperature. Okay. Remember, it wouldn't give me an accurate temperature because I've already told you that this surface here represents a pixel that contains material at 2 different temperatures. If I invert the Planck function, I just get 1 temperature. I don't get 2. How thermally homogeneous the surface or how thermally heterogeneous the surface is dictates how close you are to the true temperature when there are multiple sub-pixel radiating components. Okay. So let's just look at that example a little more. So curve 6, which is the orange curve. So this is exactly the same as the red curve, except all I've done now is taken that big lava flow, which used to fill the pixel, and I've shrunk it down, so it now only occupies 3% of the pixel. So the orange curve is this, shrunken down, so it fills 3% of the pixel, with the remaining 90% of the pixel radiating at this temperature, or basically equivalent to curve number 4. So you can see here now, I can still easily distinguish this pixel containing this small active lava body. I can still easily distinguish it from the pixels that are surrounding it in the mid-wave infrared and the short-wave infrared, right? This pixel radiates energy in the shortwave infrared, but Earth's surface isn't hot enough to radiate in the shortwave infrared. So it'd be easy for me to detect that pixel and also quantify the volcanic radiance because I would have no background contribution. In the midway part of the spectrum here, again, I've got an order of magnitude separation between the lava pixel and the pixels surrounding it. So again, I could do a really good job of detecting that pixel and isolating the volcanic component of the radiance I measure. But if we look here, in the long wave infrared, I really don't have much separation for that pixel between the target pixel, the lava pixel, and the background pixel. Okay, so I would have a tough job detecting this pixel and distinguishing it from background pixels that I don't care about. So that's the detection part. Now, if I wanted to work out the temperature of this ground, I would also have a hard time because once I've corrected for emissivity and atmospheric effects for both the lava pixel and the ground around it, you know, there are going to be, if you like, some error bars or uncertainty on these curves, which mean that, you know, it's going to make it hard for me to distinguish the pixel from its background and isolate the volcanic radiance from the background. Okay. If I extend this further, so let's look at what I had for curve 7. So, so curve 8, let's have a look at curve 8. So curves 5 and 6 and then 7, these are all for active lava bodies. So I missed curve 7. So curve 7 is a lava body at 1400 K, which occupies only 1/100% of the field of view, with the remainder radiating at 15 degrees C. So curve 7 might be, if you went up to the summit of Mount Etna and one of the summit craters was active and it had a strombolian vent that had some lava in it, and the vent was maybe 30 meters in diameter, the satellite would measure curve 7. So again, it would be easy for me to detect that in the shortwave infrared and the midwave infrared. Very hard for me to get separation or detection or good data in the long-wave infrared because I really get no separation in terms of the radiance that pixel is radiating from its background. For geothermal type features, so curve 8, the situation is even harder because they're lower temperature. So curve 8 might be a fumarole field at 100 degrees C, which occupies 1% of the field of view, with the remainder radiating at 15 degrees C. You'll see curve 8 is barely different from curve 4. There's pretty much no chance I'll be able to distinguish that pixel from its background, okay? Because I get no separation in terms of the radiance that it emits, okay? Curve 9 is exactly the same as curve 8, but now I've made that fumarole field occupy half the pixel instead of 1% of the pixel. So now I get separation at all wavelengths, okay? So I could detect that fumarole field if it filled half the pixel because I could distinguish it from the background. So the background is curve 4. The pixel with the fumarole field in it, which occupies half the pixel, is curve 9. And at each of these wavelengths, I get good separation, okay? But you'll see that my signal to noise is lower for the fumarole field than it is for the lava flow, right? So any detection or quantification process is dependent on signal to noise ratio, right? The higher the signal and the lower the noise, the better science you can do. So the hotter the target, the more SNR I have, the colder the target, the lower signal to noise ratio I have. This is complicated based on whether you acquire the data by nighttime or by daytime. So I've been talking about nighttime data. So if we take this pixel here, this lava flow, so this is a lava flow filling the pixel at 600 K, and you can see it's easy for me to detect it in the shortwave infrared at nighttime, right? Because the Earth doesn't glow in the dark, but this lava flow radiates a ton of energy at this wavelength, making it really easy. I've got orders of magnitude separation in terms of the radiance it radiates compared to its background. But not if I turn the sun on. Right, so these curves here, 9 and 10, these show the amount of light reflected from a dacite and a basalt when the sun starts shining on it. So if I take a lava dome at Unzen volcano at night, I might be able to detect it using shortwave infrared energy, shortwave infrared radiance measurements. But during the day, I can't because the ground, the dacite, will reflect almost as much energy as it emits. And now I have another terrible signal to noise problem. The reflected light is noise, the emitted light is signal. And if I have a reflected component, which is equal in magnitude to the emitted component, then I really can't do a great job of separating out the volcanic radiance, which I care about, from the reflected radiance, which I don't care about. Again, the spacecraft just measures photons at a particular wavelength. It doesn't distinguish between whether they're reflected or emitted. That's something that you have to do using the kind of rules that I've just described. Okay, so I'll end there. So we can have some questions if you like, Ryan.
Sure thing. Makes me appreciate my centimeter size drone pixels.
So I don't know how to get back to the, oh no, hang on.
So
okay,
there's a couple questions. One was, if I understand correctly, I'll just read it. Consider Mount Fuji. What will the thermal values be like for this? And then I don't fully understand the rest of the question. I think trying to understand thermal remote sensing with an example of Mount Fuji.
So at the moment, I don't believe Fuji is active, right?
I don't think so.
Yeah, so Fuji is not active. So if you take a satellite image of Mount Fuji in the long wave infrared, say Landsat, you convert dN to radiance, you plug it into the equations I've shown you, you correct for the atmosphere, and you correct for the emissivity, you'll get a pretty accurate estimate of the surface temperature of the ground within that pixel. Okay. Now, if you wanted to work, if you suspected that magma was rising at shallow depths, and sorry, I've been talking for days on Zoom. Magma was rising at shallow depths, and you were expecting that that might translate into an invigoration of a shallow hydrothermal system, then you might expect an area near the summit to get slightly hotter, right? Now, whether you could detect it or not, if you made measurements on successive days or successive months, if you apply the rules I've given you, you stand a chance of detecting that small increase in temperature. Okay, you've got to correct for the atmosphere, and the atmosphere changes every day, so you've got to get a new atmospheric correction every day. It's not as important for tall volcanoes because the higher up you are, the more atmosphere is beneath you, right? So in Alaska, you almost don't have to correct for the atmosphere because there isn't much atmosphere up there anyway. But you have to correct for it. Emissivity, shouldn't change that much. But what you are faced with in that situation is what I showed before. So you can still see my slides if I do this, right, Ryan?
Yes.
Yeah. So the problem you would be faced with would be this problem. You would have a background, which would be the black curve 4, for example. That's the ambient temperature ground at the top of Mount Fuji in the absence of a volcanic heat source. If you only add a small amount of volcanic stuff at 100 degrees C, you get the blue curve, right? You get the curve, which is the blue curve, which is a volcanic feature at 100, which only occupies 1% of the field of view. Now, the question would be, given the accuracy of your atmospheric correction and given the accuracy of your emissivity correction, can you reliably distinguish the blue curve, curve 8, from the black curve, curve 4? The larger and hotter your feature becomes, the more easily you can make that distinction. But again, in that example, you have a horrible signal to noise problem because the signal is really small compared to the background. So maybe that answered the question.
Okay, fantastic. I'll try to interpret this other question. I'll just read it and I'll let you interpret it. To what extent using a single target for correction is enough, especially if it is a mixed pixel?
Okay, so I'm going to talk about that throughout the whole next session. Yeah, great. I mean, if I've got ground, if I've got a pixel which contains material at 300 Kelvin, half of it's at 300 Kelvin, and half of it's at 1,000 Kelvin, and I use the equations I've just given you, I'm going to get one temperature which will be neither 1,000 Kelvin or 300 Kelvin, right? And it won't be in the middle of those things because the mixing is nonlinear. So yeah, you're right. How can I work out? How can I unmix that mixed signature? So remember, the spacecraft makes a measurement of, well, it doesn't measure photons because you can't measure a photon, but photons leave the surface, right? And we convert it into a photocurrent. And that photocurrent is proportional to the photon flux which arrived at the detector. But the detector doesn't know whether those photons came from something at 300 Kelvin or 1,000 Kelvin. It doesn't know how many of them were radiated by the atmosphere. It doesn't know how many of them were reflected from the surface. So I showed you how to correct for the atmosphere and the emissivity last time. In the next session, I'll show you how to do that on mixing to try and estimate how many came from the half of the pixel, which is at 300 Kelvin, and the half of the pixel, which is at 1000 Kelvin.
Fantastic. There's just one comment, and people are echoing it. This was absolutely one of the very best explanations I've heard so far about this topic. So it was very good. Thank you. And one other question, asking about applications of thermal remote sensing for detecting coal mine fires.
So, you know, the remote sensing physics and principles are exactly the same as the ones I've just described you and the ones I will describe you, right? So for coal fires, so Anupma Prakash, who is now the dean of something or other, Alaska Fairbanks, so she published several papers. I think most of them were in IJRS, but she published a bunch of papers on coal mine fires. So a coal mine fire, you know, when it's beneath the ground, you see the surface expression of a subterranean fire, right? So that's going to be a low temperature anomaly. So that's going to put you, sorry, what am I doing? So that's going to put you here, right? A subterranean coal mine fire where you have a subtle elevation of surface temperature of 10, 50, you know, whatever degrees. That's going to put you here in this signal to noise limited part of the curve. If these things break out at the surface, then you will quickly move to this part of the diagram, where now you've got actual flaming material or hot material visible to the sensor, which is going to be far easier for you to detect and quantify the excess radiance above the background. So I don't know, to be honest, I know little about coal fires. Are they mainly subterranean, or do you see hot stuff at the surface? Maybe the questioner can tell us that.
I'm not sure, but someone has provided a clarification that according to the meteorological agency, I guess in Japan, Mount Fuji is still classified as an active volcano, although not currently erupting to my understanding right now.
Right, yeah, so there's that thing, that Holocene active, right? It's the funny thing about geology, we have such a small sample size. You know, there's a reason they take the mickey out of geology in the Big Bang Theory. You know, we have such a small, we try to predict the activity of volcanoes that are 500,000 years old based on a half decent measurement record, which maybe extends 10 years.
Exactly right.
And that is a big problem.
Okay, I'm not really seeing any other questions at this point.
Okay, so should we have a 5-minute break? I'm going to get a glass of water or something, and then we'll. Oh, we got a question. I can take this while I'm getting my water. I'm in my house. I can just go to the kitchen. So if you read it out.
All right, I'm trying to see a question here. I mostly.
Somebody raise that hand.
Hi.
Oh, raise their hand. Okay.
Yeah.
Yes. Go ahead.
Yeah, I have a question like, is there any effect of sunlight or cloudy sky in terms of emissivity or the surface temperature of the volcanic areas or the lava flows?
Clouds. Well,
effect of sunlight and clouds.
So the clouds are, if a cloud is between you and the target, you will measure the temperature of the cloud, right?
Yeah.
That's not, you know, sometimes you can have thin cirrus clouds, which then you will be seeing, there'll be some emission from the cloud, there'll be emission from the ground, some of which will be absorbed by the cloud. There'll be emission from the cloud, and what you'll measure is the sum of the emission from the ground minus what was absorbed by the cloud plus the emission from the cloud, right? That's, you know, really hard to correct for. So those are the cloud effects. If it's dense cloud, you measure the cloud because the radiation from the ground doesn't reach you. If it's thin, then you can get a mixture of the two. In terms of the satellite, you know, the measurement the satellite makes is incredibly precise because these things, they spend a lot of money on these things and they're very well calibrated. So when you convert, but you know, the thing you get when you use the equations I just showed you was similar to go from dN to spectral radiance. that measurement of spectral radiance is wildly precise. Okay, there's nothing wrong with that measurement of pupil planar radiance. The uncertainty comes in when you say, okay, well, I know I lost some photons to the atmosphere. How do I add them back using ModTran? So that's a noise term. The emissivity, you may know it, you may not know it. If you go to NV, oh, sorry.
So during a sunny day, like it will be a different, like than the cloudy day. May affect on the.
So it will heat up differently, right? So if you imagine, so yeah, let's take the case when. Well, no, actually, it's not really the cloud. Let's say time of day. So when Terra Modis goes over Kilauea in the morning, it goes over at about 10:30 in the morning. If Modis looks at my yard and makes a measurement of radiance, if I correct for the atmosphere and the emissivity, I'll work out a temperature. When Aqua Modis goes over in the afternoon, about 4 hours later, the sun will have heated that ground up, right? If I take the Aqua Modis measurement and convert to a measurement of temperature, I'll get a higher temperature because the ground has been heated up by the sun.
Yeah.
Yeah. So so the hydrothermal case that I just mentioned, that's one thing you do have to correct for, because remember, say I have a pixel which contains, say my shirt's a pixel, right?
Yeah.
And one of my little buttons is a fumarole that's radiating at 100 degrees C, right? At 10:30 in the morning, the spacecraft measures the energy from the ground around the fumarole field plus the energy from the fumarole field, right?
Yeah.
If I go over later in the afternoon, imagine the fumarole hasn't changed. It's still the same size and it's still radiating photons consistent with it being at 100 degrees C. But say the area of ground around it has increased by 20 degrees C because of solar heating. It will now be a lot harder for me to isolate the photons associated with the fumarole compared to the energy radiated by the background because of the solar heating component. So yeah, you've got to correct for that in these data sets. If you're looking at low temperature phenomena, if you're looking at an active lava flow, say that, the Bardarbunga flow in Iceland, what was that, 2014? That thing was, so it's the front slide of my presentation. So let's just have a quick look at it, just for example. So this thing was absolutely gigantic, right? So if I'm trying to work out the energy, the volcanic energy, say I've got a pixel which fills this, this photograph. I've got the energy from the lava flow, which I care about, but then the ground around it is also emitting photons, right, based on its temperature, which at this time of year would have been about 0 because it was pretty cold. If you use those equations that I showed you and calculate the radiance from something, this is bright, this is hot, this is like 1,000 degrees C. If I work out the radiance from this, because it's so large at the scale of the pixel, and then I work out the radiance from the ground around it, I'll find that this dominates the satellite component. So for something large and hot, it's not that important that you do a precise background temperature correction. For something small and cool, it becomes way more important that you do an accurate background temperature correction. Again, it's all signal to noise.
Thanks a lot.
So are there any other questions? Should we move on, Ryan?
Yes, I don't see anything at this point, so please.
Okay. Let me just find my other. Let's go make this small.
Oh, there's one that just popped up. So maybe before you get started.
Okay.
The question is, we can use reflectance or emissivity spectra on sensors to make mineral maps, but can we map minerals based on temperature? Is there some kind of correlation?
No. So not based on the temperature value. I mean, you take an emission spectrum, and based on variations in the amount of something emits as a function of wavelength, that gives you an emissivity spectrum, which is the equivalent of a reflectance spectrum. And the troughs in that emissivity spectrum correspond to the wavelengths at which the material characteristically absorbs energy. So, as I said, in a quantum world, that's basically photons which can move electrons between the populated and allowable energy levels of the ion and its bonds. So they're wavelength specific, they're Z number specific, and that's how we can fingerprint materials on emissivity spectra. If you're a wavelength person, then that's those Lorentz forces that you may have read about years ago. But the temperature, no. I mean, it's not, when you're doing chemical mapping using thermal infrared data, you don't convert to temperature. You convert to radiance, and then you convert to emissivity, and then you use that. You search your spectral library for a matching emissivity spectrum. Okay, so I'll get going on this. So again, this is kind of general stuff. So if you're an expert, then you know all about this. But I thought I'd break this down into topics related to the analysis of high spatial but low temporal resolution data. So data like Landsat, data like ASTER, data like EO1, data like the Prisma data that Fabrizio talked to you about yesterday. Basically small pixels, but you don't get them very often. Okay. And then the next part will be the opposite. So high temporal resolution, but low spatial resolution data, big pixels, but you get them really frequently. Remote sensing, with volcanoes has typically been broken down, or, has typically been divided between those two camps. And I'll explain why. The distinction between the two is increasingly blurred. Because we have real-time data from high-resolution satellites, yet constellations of spacecraft means that we can get small pixels relatively frequently. So, those things being considered, this is just a convenient way of breaking it down. So basically, we have satellites like Landsat, which acquire 30-meter, 100-meter pixels every 16 days. And then we have sensors like ABHRR or the GOES ABI or MODIS or VIIRS, which are, give us 1 kilometer pixels, 2 kilometer pixels every hour, every 15 minutes, every 12 hours, every 24 hours. So how do you work out which volcanic processes are best suited to analysis by these different types of remote sensing data? Well, it depends on a lot of things. So is your target small or large? Are you interested in studying these kind of Pahoehoe pads at Kilauea volcano? Not that there are any anymore, but this is pretty small and hot. Or are you interested in studying the kind of lava flows you get at Niamaragira and Mount Etna, which are just huge and hot? Or are you interested in studying lava domes? So this is Santa Maria volcano in Guatemala. This is the active lava dome, but it's pretty small and it's rather cool. This is mafic lava. This is mafic lava. This is felsic lava. The surface of this is not thermally renewed very quickly. The surface of this dome isn't churning in the same way that the surface of this mafic flow is churning. So this is small and cool. It's still active lava, but if you want to study this, you would use a different type of data than if you want to study this. The last example, if you're interested in studying hydrothermal volcanism or geothermal features, these are small and cool, really small and cool, right? So you'd use different data to study this to this. The data acquired by night or by day. So this is the dome at Soufriere Hills on Montserrat by day on the right and by night on the left. So you can see here, going back to the last slide, sir, here, for these pixels here, I'm measuring the amount of light reflected from the surface. For these pixels here, I'm measuring the amount of light reflected and emitted from the lava dome. But if I look at night and I turn the sun off, I don't see any reflected light. All I see is the emitted light. Okay, so this is, if you're interested in studying hot volcanoes, nighttime data is fantastic at these wavelengths. This is shortwave infrared data. Are the data required at high or low spatial resolution? Well, this is Soufriere Hills again, I think, or it might be, well, obviously I can't work it out. It's a nighttime data scene. This may be Erterale, because we've got two sources. But this is a nighttime Hyperion shortwave infrared false color composite. And you can see that because this thing is really hot, it's radiating lots of light at the shortwave infrared part of the spectrum. Okay, so it's really easy for me to detect this active lava and distinguish it from surrounding pixels, because the surrounding ground, as I said, the Earth doesn't glow in the dark. It isn't hot enough. So it's very easy for me to detect those pixels and also quantify the volcanic radiance, or the photons which are associated with the lava in this example, because they're the only things that the spacecraft measures at night. Now, I can do this at high spatial resolution, but this is the same target acquired at about the same time in MODIS data. And you can see, I can't work out that there are two radiance sources from the MODIS data. This box is a 1 kilometer MODIS type pixel, but I can still detect that there's something there, right? I mean, this is the ground around the volcano. But if I was trying to detect whether this volcano was active or not, these 1 kilometer data would tell me, wouldn't they? Because I can see that there's a pixel here which has a whopping great signal, surrounded by a load of pixels which aren't giving me a high signal at all. I plotted this up here. This depends on wavelength. So these are some ATSR pixel maps from the summit crater of Mount Etna from 1998, I think. So on the left is 1.6 microns. In the middle is 4 microns. So the shortwave infrared on the left, mid-infrared in the middle, and long-wave infrared on the right. So I'll show you in a couple of slides. At the time, there was just a series of vents in the summit craters. It was a nighttime image. This is in DN space and temperature space, but you can see, you know, at 1.6 microns at night, it's really easy for me to detect the presence of those summit craters, even though those craters were far smaller than the 1 kilometer pixel size of the ATSR sensor. So each of these pixels is 1 kilometer on a side. If we look here in the long wave infrared part of the spectrum, what these gradients are telling me, this is telling me the temperature of the ground at the summit of the volcano. So this is kind of the summit plus or minus 3 kilometers in each direction. So the long wave data are telling me the temperature of the ambient ground. Okay, I really can't distinguish the summit craters that well. So this gets back to that signal to noise problem. You know, there's the summit crater pixel, and I have a slight elevation in temperature, but it isn't that great. If I wanted to isolate that pixel using some kind of thresholding metric, it would be quite difficult because its radiance characteristics are very similar to the radiance characteristics of the ground surrounding it. At 3 microns, it's much easier for me to isolate the volcanic signal from the background signal, because the volcanic signal is radiating more energy at this wavelength than at this wavelength, even though it's way smaller than the pixel size. And then finally, you know, at 3 microns, I'm measuring emitted and reflected energy. At 1.6 microns, if this is at night, there's no reflected energy. I'm just measuring emitted energy. And because only the lava is hot enough to radiate significant amounts of energy in shortwave infrared, it's very easy for me to detect the volcanic radiance. Huge signal to noise here, terrible signal to noise here, okay signal to noise here. So in terms of whether you use high spatial resolution data or low spatial resolution data, whether you look at it by night or by day, and which wavelength you look at, there are many ways to skin a cat. So there are lots of different data sets available to you. You should just choose the best one that helps you retrieve about your target that which you want to retrieve. So, you know, there have been a lot of people who've kind of grabbed onto a particular sensor and used it their entire career. Whereas I've always used whatever I've got my hands on. So in my PhD, I was using Landsat data, AVHRR data, and ATSR data. Then I was on the EO1 science team, so I started using hyperspectral, high-resolution data. I used some GOES data, which is the geostationary data. MODIS science team, so I've used MODIS data. I'm now on the VIA science team, so I use that. I'm on the ASTA science team, so I use that. I've never done drone stuff, but I've done ground-based spectrometer measurements. You know, don't get wedded to a particular sensor. There are lots of sensors out there that acquire data at low and high spatial resolution by nighttime or daytime, in the short wave, the mid wave, and the long wave, once every 2 weeks or once every hour. You should just choose the volcano you want to study and then get all the data you can and then piece it all together. The good news is they all calibrate to spectral radiance, so you have a common unit that you can compare across these different sensors. But typically, getting back on topic, sorry about that, high spatial resolution data have generally not been acquired frequently enough to do time series analysis. So that's less true now, but it was definitely true until about the year 2000, well, until about 5 years ago. So just an example, when I was doing my PhD, this is, so on the bottom is a Landsat image of the Etna 9193 flow. So these are good looking data, right? You can do a lot of work with these data, there's lots of detail. On the top is an ATSR image of the same volcano acquired a few hours earlier. Okay. So I'd rather have these data than these data, right? Because this gives me more spectral resolution, more spatial resolution, and I can do a lot more work. On the right, I've just plotted up how frequently we got those data. So at the time, ATSR had, these are the number of cloud-free data sets available throughout that eruption for AVHRR and ATSR and Landsat. So for AVHRR and ATSR, there were 60 cloud-free data sets acquired during that eruption. So 60 images like this. For Landsat TM, there are only 5. So even though Landsat went over every 16 days, it acquired an image of Mount Etna every 16 days. But on all but 5 occasions, there were clouds in the way. And this is a problem. I mean, when people design missions, you plan on the fact that the Earth's surface is cloudy 2 days out of 3, right? So, you know, when we only had data like Landsat and ASTER, and there were single sensors on polar orbiting spacecraft, which meant that the repeat was 16 days, clouds would mean that we didn't get these kind of data frequently enough to build time series. Okay. You know, there's work you can do. If you have 5 observations of a 2-year-long eruption, you can do some work, but you can't do time series analysis that well. What you can do is detailed analysis of what's going on in these pixels, which you can't do here because I don't have much detail in these pixels, right? So for that reason, high spatial resolution data has often been used for detailed analysis and proof of concept type studies, but not for time series analysis. That's kind of changing. So this is an example. I should say a lot of the examples in here, this isn't, I'm not being wildly egotistical. These examples are often drawn from papers that I've been part of, mainly because I have the figures and it was easy for me to put them into a slide set. So I'm not telling you that I'm the only person who's ever published in this area. You should go away and search the literature. There are tons of papers. What you see here is because I had the figures on hand because I was on the publishing team that put them together. But anyway, back to this. Our ability to do time series analysis with high spatial resolution data is improving now that we have, for example, real-time delivery of high resolution data. So this is a sequence of ASTER images. These data now come down in virtually real time. So you can get them within hours of the spacecraft making the measurement. At the moment, we have Landsat, we have Sentinel, we have constellations of satellites now, which previously, you know, in the 80s, we had Landsat, we had one Landsat, and it went over once every 16 days. Now, with a couple of Landsats and the Sentinel spacecraft, we get similar data acquired every few days, not every 16 days. So this makes it much easier to build time series using high spatial resolution data. We also have Google Earth Engine. So if you wanted to work out the temperature of the fumarole field at Volcano using Landsat data between 1984 and the present day, you could do that in half an hour. Just write a little JavaScript and you could analyze all that data in the cloud and get yourself a result really quickly. So typically, we've used high spatial resolution data for detailed analysis and concept studies, but you know, with the advent of constellations and also cloud processing, it's becoming easier to do time series analysis with high resolution data because more data are available, we get them more quickly, and it's easier to analyze the number of pixels, right? If you have a time series of 30 years of Landsat data, that is a lot of data. You know, you couldn't download that over FTP and analyze that. You could, but it'd take you months to download the data. But using things like the cloud, it becomes easier and more tractable. So what I'm going to talk to you today is basically how you can use the high spatial resolution data to do detailed analysis of lava surface temperature and then derive parameters, including cooling rate. Okay. And basically, because we just get so much more detail. So this is on the left. This is an image of Mount Etna. Here's a Landsat image of the summit craters, northeast crater, La Voragine, Boccanova, southeast craters over here. I can see what's going on in these individual craters if I use Landsat or EO1 or Aster. This is a 1 kilometer box equivalent to MODIS. So all of this is taking place at the subpixel scale with MODIS. And then if I go to the next generation of GOES advanced baseline imager, the pixels are 2 kilometers. And as just an example, here are some simulated data that I made. Here are the lava flows at Kilauea simulated at 60-meter data on 3 days. If I convolve that to MODIS resolution, you can see if I want to do detailed analysis of these lava flows, it's far better if I have high spatial resolution data than if I have low spatial resolution data. Okay. So going back to a question that we just had in the question section. So as I said, if the temperature of the ground within the pixel is thermally homogeneous, it's really easy to use the equations and the approaches I just showed you to work out the temperature of that surface from the satellite data. We go in, we find a pixel. It's thermally homogeneous at the 60-meter scale of this Landsat ETM plus pixel. I take the DN, I use the equations I showed you in the last slide set, and I convert to spectral radiance. I correct for the emissivity and the transmissivity. I plug it into this equation using the constants I showed you and the wavelength of Landsat band 6, and I get a kinetic temperature. Sorry, I get a brightness temperature, but because I've corrected for emissivity and transmissivity, that brightness temperature will be very similar to the kinetic temperature of the target. And it doesn't matter whether that surface is hot or cool. I just take a measurement of radiance at whatever wavelength I want, correct for the atmosphere, correct for the emissivity, plug it into this equation, and I will get a pretty accurate estimate of the kinetic temperature of that surface. Okay, because the surface is thermally homogeneous at the pixel scale, which means if I made a measurement here, I'd get 30 degrees C. If I made a measurement here, I'd get 30. If I made a measurement here, I'd get 30. You know, if this is a pixel, if I'm in a boat sailing around in this pixel off the coast of Kilauea and I dip a thermometer over the side, I'd measure the same temperature here, 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 right? So that's okay. The satellite data is going to give me one temperature, but that's fine because the temperature doesn't vary at the scale of the pixel. So my temperature is a good temperature. That's fine in volcano remote sensing if you're doing something like this. So if you want to measure the temperature of volcanic crater lakes, they're quite well mixed, right? The water overturns, it's quite well mixed. So it equilibrates within a narrow temperature range at a particular instant in time. So you could, this is what one of my old postdocs did. You can go in, you can get a time series of Landsat data. So he did this in Google Earth Engine. You could get a time series of Landsat data for 30 years for each of these lakes, and you can work out how its temperature varied over time. And he did this basically using exactly the same techniques that I've just shown you. So pretty easy. It's harder if you're looking at active lava bodies or coal fires or wildfires, okay? So this is a Landsat image. This is a shortwave infrared color composite. These are the active lava flows. The spatial resolution of Landsat is 30 meters by 30 meters at these wavelengths, right? So if I do what I've just shown you, if I take the DN from this pixel and I convert to radiance and I correct for the atmosphere and I correct for emissivity and I plug it into the Planck equation, I will get one temperature for this pixel, right? But I know if I was there on the ground and I looked around, I'd see something like this. There'd be small lava flows surrounded by radiating at 600 degrees C, 800 degrees C, 300 degrees C, surrounded by just inactive lava, which is radiating at 30 degrees C. So the satellite data would give me one temperature, but I know there are many more temperatures within that pixel. So really that temperature is garbage, right? It doesn't mean anything. And the problem is it doesn't matter what scale I look at, I find a continuum of temperatures. So this is a single Pahoehoe lobe, but if I get close in and I look at the front, I'll find that I've got relatively cool crust, relatively hot lava, fresh lava from the flow interior. And then I have these areas which are halfway between fresh lava and crust. So again, And if I back out one temperature using the techniques I've shown you, it will be a junk temperature. I'll get one temperature which won't represent any of the temperatures which actually occur within that pixel. Okay? So that's a problem. So how do we fix that? Sorry, I'm just take a drink. So there's a technique called the dual band approach. So if you Google Rothery, Francis and Wood, 1998 JGR, you'll find a paper they published which basically popularized this technique in the volcanological community. Basically, how do you unmix the mixed spectrum from a pixel containing an active volcanic feature so that you can more accurately work out the temperature of the lava? If you go back before that, there was a paper by Jeff Dozier from the early 80s, which was in photogrammetric engineering and remote sensing. It's referenced in the Rothery paper, which did the same thing, but they were looking at snow and ice and cloud. But this simple thermal mixing was pioneered by Rothery in the 80s. So I'm just going to describe to you how it works. So all the curves you see here, you could produce using the equations that I gave you in the last slide set. So there's nothing complicated here. So let's start up here. Imagine I have a pixel, the blue pixel, which is thermally homogeneous and has material, is entirely filled with material at 325 Kelvin, right? If I compute the spectral radiance at each wavelength for a temperature of 325 K, I get the blue curve, right? If I have a pixel next door to it, which is filled with active lava, so this is ambient ground, and this is a pixel filled with active lava, and I do the same exercise at each wavelength, but instead of using a temperature of 325, I use a temperature of 1300, I get this red curve, right? So a pixel at 325, I get the blue curve, pixel at 1300 K, I get the red curve. And if these pixels are thermally homogeneous, I can just take a measurement of radiance at each wavelength and use Planck's equation to get a temperature. And it will be a good temperature provided I correct for the atmosphere and the emissivity. But this is rare, right? This is more what lava flows look like, right? We have a small lava flow surrounded by ground, which is at ambient temperature. Okay, so we have a sub-pixel size lava flow. So that might be this. Okay, so this is a cartoon, but what I'm showing here is ground at 325 Kelvin, which is in blue. And in there, I put a tiny amount, so this square here, and I blow it up, I put a tiny amount of hot lava at a temperature of 1300 Kelvin, which fills 1/100th% of the pixel. Okay? So hot stuff, a tiny amount of hot stuff, surrounded by, tiny amount of hot stuff, surrounded by a load of cool stuff, right? Now, remember, the spacecraft only makes a single measurement of radiance at each wavelength. So what does the spacecraft see? And it doesn't know whether the photons came from the hot material or the cold material. The photons arrive, it converts them to a photoelectric current, and that gets converted to a dN. So you just get one dN, and that dN is proportional to the energy from the whole pixel. It doesn't tell you anything about the energy from what was within the pixel. Okay. So let's work out what the spacecraft actually measures at each wavelength. So basically we weight by area, as you can imagine. So you know, if they're a geologist, when you look at a mixing line, you weight the different components, right? You take a certain amount you take a certain starting composition, and you extract a certain volume of a particular type, a certain mass of a particular type of crystal, and what you can easily work out the composition of the liquid that you're left with, because it's just a simple mass balance, right? It's just linear mixing. We do mixing in this case, we mix photons, but the mixing is non-linear. So I'll just describe how that happens. The way we would predict the single dN value that we measure from a pixel in this instance, where we have a small hot thing in a pixel surrounded by otherwise cool material, is we would say, okay, well, the ground at 300 Kelvin fills 0.9999%, sorry, 0.9999 of the pixel. So what we would do is we would take, at each wavelength, we would take the radiance value of this blue curve here, and we would multiply it by 0.9999, and we would plot that here. And we just do that at every wavelength, and we end up with the blue dashed curve. We would then repeat that exercise here. We would, for each wavelength, we would take this value of radiance for the red curve, but we would multiply it by 0.0001, okay? And that would give us the red curve. This red dashed curve here. So what we've done is we've said, okay, well, if the pixel's filled with material at 1300 Kelvin, I get the red curve. But I know the amount of material at 1300 Kelvin is actually tiny. It's this amount. So I have to scale this curve by this number. Okay? And if I do that, I get the red curve. Okay? So this is actually what the ground would radiate from this pixel. Right? This single pixel here, because the amount of lava in the pixel is so small, it wouldn't radiate 10,000 watts per meter squared plus radian at 2 microns. It would radiate 1 watts per meter squared plus radian per micron at that same wavelength. Okay? Because the amount of material at this temperature is tiny. Now you'll see the blue curve didn't change, right? The red curve changed a lot because I have such a small amount of this. The blue curve didn't change much at all, okay? Because the material at 325K occupies the vast amount of the pixel. So I've taken this and I've multiplied it by a value which is virtually 1. So this curve doesn't change. So this is how the tiny amount of hot lava would radiate energy from this pixel, and how the ground surrounding it would radiate energy from the same pixel. What the spacecraft would measure would not be the red curve or the blue curve. It would, well, the energy radiated from the surface isn't in fact this and this, it's the sum of these two things, right? So if I add the red curve to the blue curve at each wavelength, I get the green curve. So you can see here, and I mentioned this before, something at 325 Kelvin isn't hot enough to glow, right? The Earth doesn't glow in the dark. So it doesn't radiate light at 1 micron. But the lava, it's so hot that even though it's so small, it still does radiate some energy, even at these wavelengths. So in this part of the spectrum, the green curve equals the red curve, because I just have red curve, no blue curve, right? Because the ground isn't radiating at these frequencies, the lava is radiating. In the long wave infrared part of the spectrum, it's the radiance from the ground surrounding the lava that dominates, okay? Because I don't really have any emission, I have negligible emission from the lava at these wavelengths, right? Really not much. The emission from the ground surrounding the lava dominates. In this part of the spectrum, at around 4 microns, I get a mixture of red and blue. I get a mixture of the energy radiated from the ambient surface and the energy radiated from the hot lava, right? So I get the green curve. So the spectral radiance at any wavelength from this mixed pixel is the green curve, which is made up as the sum of the red curve and the blue curve. And the red curve and the blue curve are derived by taking the end member radiance curves and then scaling them by the proportion of the pixel that they occupy. So that's just this simple mixing relationship here. I take this curve and at each wavelength multiply it by that number and I get the red curve. I take the blue curve and multiply it by that number at each wavelength and I get the blue curve, and then I add them together and that gives me the green curve. Okay. Now what Rothery and others did is said, well, okay, we still only get a measurement of radiance at 1 wavelength. Okay, so what I have to do is try and unmix that, because if we look at this pixel here, this is a single Landsat pixel, and I have lava at a hot temperature, which occupies a certain fraction of the pixel. And then I have ambient temperature, I have crust, sorry, surrounding that lava. So this is the orange stuff. And then I have the lava crust, which is at a lower temperature, which occupies the remainder of the pixel. Okay, and they established this thing which they called the dual band method, which was the Dozier bispectral method, which basically says the radiance at any wavelength is equal to the radiance from the hot component multiplied by the area of the pixel it covers, or the fraction. Okay, so F equals this number, plus the radiance from the crust radiating at the crust temperature multiplied by the area of the remainder of the pixel. Right, so this is assuming that the lava fills the pixel and there's crust occupying one area at one temperature and cracks occupying the remainder of the pixel at a much higher temperature. Okay. Now, the way I can work out this, the problem here is I have 1, 2, 3 unknowns, right? I don't know the hot temperature. I don't know the crust temperature, and I don't know the area of the pixel that the cracks occupy, right? So I have 3 unknowns, and I only have 1 known. Okay, so that's not a good way to solve an equation. So what Rothery did was said, well, okay, we have Landsat band 5 and we have Landsat band 7. So we actually have 2 knowns because we make one measurement here and we make another measurement here. Okay, Landsat band 5, Landsat band 7. So we have 2 knowns. We still have 3 unknowns. So what Rothery, and in particular Oppenheimer after that said was, well, we've got 3 unknowns. So to solve this pair of equations, we have to get to 2 unknowns. Otherwise we can't do it. So what Clive did was said, well, this temperature could be highly variable, right? When active lava is erupted, it's erupted at the, something close to the eruption temperature or the molten lava temperature. So it starts at, say, 1,000 degrees C, but it instantly starts cooling. And over time, it cools to one temperature, then another temperature, then another temperature, then another temperature. So based on the age of the lava, the crust temperature is very variable, right? So Clive said, well, this temperature should be much less variable, right? The temperature of the orange stuff should be not very variable at all because it should be close to the eruption temperature, which really should only vary with the temperature of the chemistry of the lava. So mafic lavas are erupted a couple of hundred hotter than a felsic lava. So Clive said, I'm going to assume TH is 1,000 degrees C. I'm going to assume TH is 1050 degrees C if I'm at Etna, and I'm going to assume it's 1140 if I'm at Kilauea. And if I do that, I now have 1, 2, just 2 unknowns, 2 knowns. So I can solve this system of equations. And if I do that, I can work out the temperature of the crust, Tc, and I can work out the area of the pixel that the cracks occupy. Okay, so that's the dual band method that's been applied for years. I mean, I've used it, Harris used it, Oppenheimer used it, Rothery used it, everybody's used it. And this is basically the explanation of it. Okay. So to answer the person's previous question about what you do if you have a mixture of temperatures within the pixel, you do what I've just described. Well, this is one thing that you can do, okay, to unmix the temperatures. Now, when they were doing this, the development of this technique was driven to a certain extent by the data available. So, they built a model to use Landsat data. So Landsat really only gave you 2 spectral measurements. So they could only have 2 spectral bands. The number of knowns could only be 2. Basically, if a surface is hot enough to radiate in Landsat band 4, it will saturate bands 5 and 7. If it's radiating in bands 5 and 7, it will saturate Landsat band 6. So they only had 2 unknowns. So they had to get back to, they only had 2 knowns, sorry. So they had to get back to 2 unknowns. So the fix they used for that was, they said, well, let's assume at 30 meters, the lava fills the pixel. If we do that, and we assume that the crust is at a single temperature, then we can assume this temperature. That's a pretty solid assumption. And we can work out the crust temperature and the area that the cracks occupy. Okay, and we can unmix that pixel. So, a problem is that lava surfaces aren't this simple. And often sensors like Landsat don't allow us to do the retrieval anyway. So what I've shown here, if we go back to the last, I'm just going to duck out of this and show you the last slide. Sorry, the last presentation. Because there's something in here that I didn't mention. So if we look at this slide, this is the relationship between DN and radiance for Landsat ETM+. Once the radiance in Landsat band, this is 4, 5, and 7. So this is Landsat band 5. Sorry, band 5 is 30, that's this channel. Once the radiance from the surface exceeds about 30 watts per meter squared per steradian per micron, the sensor saturates, so it stops measuring. Basically, the number of photons incident at the FPA are so high that the detector, we can no longer calibrate that to a measurement of radiance because that's the cutoff temperature, that's the L max, that's the saturation temperature. So in the same way that a seismometer can saturate if you shake it too hard, so these detectors saturate if you shine too much light on them. Okay. Now, to do this thing that I just described here, we rely on the fact that we know the radiance, right? But if we don't know the radiance because the sensor saturated, because the ground was so hot, then we can't apply this method, okay? Because we don't have two knowns, we have one known, because maybe this channel was saturated, okay? So what I plotted up on this curve here is contours of dN against F and T crust for an assumed hot temperature of 1000 degrees C. So these are the same equations as before, right? This is the dual band approach. These curves just show for a fixed value of TH and varying values of F and various values of TC, what the dN would be that Landsat would measure in band 5 and also in band 7. Okay, blue curves are 7, red curves are band 5.
I'm not sure that we're seeing what you're seeing on screen.
Oh, sorry, maybe I... So did you lose it when I switched back to the other slide presentation?
Yeah, we're still at the other slide presentation.
Oh, okay. Well, let me close that. Sorry about that.
No, no problem.
I guess I'm not as good at Zoom as I maybe think I am. Screen sharing. So I'll share my screen again. Sorry about that, everybody. Okay, right. This is good. Okay, see it now?
Yes, now we do.
Okay, great. So I'll go back. So you know, I was just talking about saturation. Basically, when the sensor saturates, you no longer have a known measurement of radiance. So if band 7 saturates, this disappears because this is unknown, and now I can't solve this system of equations anymore, right? If band 5 saturates, then I can't do anything because I now have 0 knowns and 2 unknowns, which is, again, is not a very good way to try and solve a system of equations. So what I plotted here for illustration is these dual band equations, which, you know, you could work these out now in Excel or IDL or MATLAB or something. I've assumed a temperature of TH, and then for various F values along this axis and various crustal temperature values on this axis, I predicted the radiance that should be measured in band 5 and band 7. And then using, for Landsat, and then using the calibrations that I showed you, I've then converted that to a dN and then just plotted these dN contours, right? So the way you read this graph is, if I have lava, which is, if I have crust at a temperature of 100 degrees C, cracks at 1000 degrees C, and the cracks occupy 0.001% of the pixel, I'll have a dN of about 10 in Landsat band 7, but I'll have a dN of about 2 in Landsat band 5. Okay, it'll be between the dN 5 contour for band 7 and the dN 5 contour for band 5. Does everybody see that? Okay, it'll plot about here, which will mean that I will maybe have one known, right? I'll have a dN of about 7 in band 7, but the surface isn't hot enough to radiate in band 5, which is a slightly shorter wavelength. So I'll have one known, maybe. I say maybe because a dN of band 7 is going to be very close to the noise floor, right? My signal to noise is not going to be very high. If I have a surface which is, the crust is about 250, and the cracks occupy an area of about 0.02% at the scale of the pixel, then my pixel will plot about here. Let's just say it's there for convenience. I'll have a dN of 50 in band 5, and I'll have a dN of 150 in Landsat band 7, okay? So now I can use the dual band system, right? I can convert those dNs to radians. I can plug them in here as my knowns, and I can solve this system of equations. And the TC value I'll get back will be about 250, and the F value I get back will be about 0.02, okay? So I can solve it. The problem with Landsat is it saturates really easily. So if I increase the crust temperature to 300 and the area of the cracks to about 10%, then my pixel will plot here. I'll get a dN of 150 in Landsat band 5, so I can still work out a good radiance value there. But I will have exceeded the saturation limit for Landsat band 7. So I'll now only have one known, not two knowns. So I can't solve the dual band system, right? So the problem with the dual band system is that basically the yellow shaded area here is the only area of this crust temperature core area feature space that it can actually be applied in. Whenever the crust is hotter than 300 degrees C, you can't use this dual band approach. Whenever the fractional area of the cracks is more than, about 7%, you can't use the dual band approach. Okay. So on the right, I've shown you a result, and this is something I generated. This shows you the result of the dual band approach for this lava flow at Mount Etna. So this is nominally the crust temperature of this lava flow on the 2nd of January, retrieved from Landsat data using the dual band approach. Oh, sorry, I've lost my pointer. These are the dual band solutions here, right? So you'll see the upper limit of about 275 is about 275. The lower limit, about 120, is kind of down here, right? These are band 6 temperatures. These are the dual band temperatures. Basically, the dual band approach is telling me that I don't have any crust on the surface of this lava flow with a temperature of 350, and I don't have any crust on the temperature with a temperature between 500 and 950, right? Which I think everybody will agree is ludicrous. Okay, that's just silly. It doesn't make sense. And the reason is because Landsat saturates very easily. Okay, so the dual band approach, it was a good starting point, but unfortunately the data aren't good enough to use it in a wide spectrum of cases, okay, because the sensor saturates, which means you quickly only have one or zero knowns, okay? So you need a more complex mixture model. So you can use hyperspectral data in the way that Fabrizio maybe showed you yesterday. So this is something that I did several years ago. This is a FLIR image of a lava flow at Kilauea. So the pixel size here is about 4 millimeters. Now, if I was applying a dual band technique, imagine this is a single pixel of a remote sensing data set. I will get one measurement of radiance from this pixel at each wavelength. But that measurement of radiance will be the weighted sum, using equations I've already shown you, of this ground, this ground, this ground, this ground, this ground, a multitude of temperatures where each temperature occupies a certain area of that pixel. Okay. So I've just plotted up the temperature histogram of all the pixels in this image over here on the right. Okay. So you can see how the dual band method isn't great, right? The dual band method is telling me I have 2 temperatures of ground within the pixel, and I'm going to solve for the cracks and I'm going to solve for the crust. In reality, the crust occupies a whole range of temperatures, and there's really no distinction between cracks and crust, right? The core material instantly becomes crust, if you like, as soon as it's exposed to the atmosphere, because it just cools exponentially, right? As this core material here ages, it becomes crust, and it gets replaced with new core material as more lava comes out from this breakout. So this is the actual temperature distribution, and all I've done here is I computed a dual band solution. So I applied Dave's method to the radiant, the integrated radiance from this pixel. And what I find is the dual band method gives me one temperature here at 570, and it tells me that material at 570 occupies 90% of the pixel. And material at 1000 occupies 5% of the pixel. In reality, material at 570 occupies about 5% of the pixel, right? If I draw a line from there, I get 5. And really, there's hardly any material at 1000 degrees C. So the dual band method gives me one temperature when I have a spectrum of temperatures. And it doesn't really tell me anything about the area of those temperatures at the subpixel scale. If I relax the constraints of the dual band method and I say, well, okay, how about if I have 3 measurements of radiance and I don't assume anything? In the dual band method, I assumed the hot temperature, which allowed me to reduce the number of knowns. Let's say I have 3 unsaturated radiance measurements, and I don't assume a crust temperature or a core temperature or any areas. I just let the method find the best fit. I let the model find the best fit to the spectrum. I get these temperatures here. It retrieves me 3 temperatures, but you'll see they're a bit more representative of the shape of the distribution than the dual band method. And then if I go to 5 and I say, well, say I've got 5 spectral measurements and they're all unsaturated and I don't assume anything, then the 5 temperatures I get back, so these are the temperatures and then these are the areas. So F and T are exactly the same as they are in these equations, except instead of, let's go back to this, instead of having 2, I've written 5 equations with a measurement of radiance at each one, unsaturated. And then I have 5 temperatures and 5 areas, and I've assumed nothing. If I do that, the solution is these gray bars. And this is a much better representation of the sub-pixel temperature characteristics within that pixel, right? I get the mode, I get the skewness, I get the fact that this is slightly bimodal, and then it gives me more information about the range of temperatures. Okay? So the dual band method was a good start, but if you want to unmix the temperatures within a mixed pixel of a Landsat image, of a high spatial resolution sensor, whether it be for a wildfire or a lava flow or a coal fire, you've got to do this kind of spectral unmixing that I'm showing you on this slide. And you've got to think about it in a different way. You can't think of it in terms of, I'm going to retrieve the 4 temperatures that are present, because that's nonsense, because there's a continuum of temperatures present, right? There aren't 4. If you look at this histogram, there's 1,000, well, 800 here, right? There are 800 temperatures. The best you can hope for is to retrieve 5 or so values and have those values mimic the distribution, the sub-pixel size distribution of radiators within the pixel. Okay, that's the best you can hope for. Now, as I proved in this example, you can do it if you have more bands of unsaturated data. Okay. So this dovetails back with what Fabrizio was maybe talking about yesterday. You use an imaging spectrometer. So this is an example from Erterale. So here are a few, these values should be familiar to you now, right? Spectral radiance against wavelength. This is a general way of stating the dual band equation, right? The mixed signal is the sum of the radiance from each temperature component multiplied by its area. So this is just the generalized mixing equation. What I'm showing here is, this is for pixel number 1. This is Erterale Lava Lake, photographed by Clive Oppenheimer. And this is an EO1 Hyperion image acquired that night. And we have 6 30-meter pixels. From this pixel, this is the radiance spectrum that I got from Hyperion in the gray curves. The white dots are the spectral values after I've done an emissivity correction and an atmospheric correction, right? So for this example, I didn't have 2 useful measurements of radiance to invert this problem. I had, I don't know, about 30 different radiance measurements, and they were all unsaturated. So I could do a much better job of unmixing. I could apply the, if you like, the dual band approach, but I didn't have to assume anything. And I had many, many more knowns to solve this system of equations to work out the unknowns. So if you read that paper, you can delve into that. But the main thing is, with something like ASTER or Landsat, you don't have many bands, and the bands you have are generally unsaturated over active lava surfaces or wildfire surfaces or a hot coal fire surface. With an imaging spectrometer, you still saturate, as I'll show on the next slide. But the good thing about an imaging spectrometer, so this is the Icelandic eruption of 2010, the one that nobody can pronounce, including myself. This is a spectrum from this really hot pixel here. So you'll see, this is saturation, right? So EO1 Hyperion is still saturated, and I had no useful data here. But Wien's law tells me that the hotter a surface is, the more radiance I will get at all wavelengths, but I'll get increasing amounts of radiance at short wavelengths. So you'll see, for this pixel, I saturate here between 1.5 and 2.5 microns. But the inverse of that is I start getting emission between 1 and 1.2 microns. Okay? So I still had tens, dozens of spectral radiance measurements here that I could use to do the fitting. So that's an important part of an imaging spectrometer. You always have lots of radiance measurements, so you're not limited to the 2 that you were with the dual band approach, and you always have unsaturated data. So that's great. You can always apply the spectral, you can always apply this spectral mixing approach because you always have many measurements. And if you're saturated here, that just means you have more usable measurements here. Okay? So imaging spectrometers are great. The good thing about being able to work out the temperatures is now you can work out cooling rates even over the hottest parts of the lava body. So here are just some examples from a few volcanoes. So if I applied, this is the cooling rate I estimated from a lava flow at Mount Etna, Sicily, using EO1 Hyperion data or hyperspectral data or imaging spectrometer data. And you can see I can work out the cooling rate along the central channel of the flow. if I tried to do this with Landsat or Aster, I wouldn't be able to work this out because this would nearly all be saturated because it would be so hot that it would exceed the measurement capability of the spacecraft. Same thing here, same thing here, same thing here. We can work out things about eruption style. So I'll skip over this a little bit. I'll just go to this. So if you remember, let's go back to this. So if you remember the graph here on the lower right, if I apply the dual band technique to this lava flow at Etna, the dual band technique tells me that this is the crustal temperature distribution of this lava flow. And I hope people agree that this is clearly nonsense. I mean, these temperatures aren't bad, but these ones are nonsense. And this method is telling me that there is not a single area of lava with a crustal temperature between 450 and 1000, which is clearly false, just fake. It's just an artifact of the fact that I can't apply the method because the sensor limits me from applying the method. But when I apply, if I take this rationale and I apply this method using these kind of data, I can work out the surface temperature, crustal temperature at every point on the flow surface in every single pixel. And if I do that here over a 6-day period at Mount Etna, I can see the surface temperature distribution of the lava flow changing over time. So you'll see here, I have some hot stuff and I have some hot stuff because this was a relatively fresh lava flow. So I had high temperature lava, young crust. You'll see it extends and I get a bimodality in this curve, right? I have cool crust and I have older crust and I have younger crust. The effusion rate decreased between day 4 and day 6. So basically new lava wasn't being exposed at the surface. The lava that was at the surface was cooling, and that's why this becomes more unimodal, right? The temperatures decrease because my lava flow is cooling. So I go from this kind of bimodal shape to this unimodal shape. The effusion rate turned on again sometime between day 6 and day 13. So now I go back to this kind of more bimodal shape, which persists over time as the lava flow increased in length as the effusion rate increased. So if you just go through this is kind of an evolution of the way this technique has developed over time. We started with the dual band technique. The assumptions were guided by the data we had available at the time. The technique is limited by the spectral resolution of sensors like Landsat and Aster because of just the number of bands, they're multispectral sensors, and the fact that they're designed to look at they're designed to measure reflectance from Earth's surface targets. They're not designed to measure the radiance levels we get from lava flows. So they saturate very easily, which means we can't retrieve temperatures using that technique for many of the pixels that we care about. With an imaging spectrometer or a hyperspectral instrument, you have more bands than you need. And if you saturate at one wavelength, that means you're getting useful radiance data at another wavelength. So you can always solve that general mixing model and get more realistic results like the ones I'm showing you here. And the good news is imaging spectrometers are coming, and there will likely be several of them. So, I was on the EO1 science team, which was the first, that was 20 years ago, and that was the first hyperspectral imaging sensor in low Earth orbit, for civilian use. It was great, it's fine. The signal to noise ratio was low, but I didn't care because the things I was looking at I wasn't signal limited, right? Lava flows emit a ton of energy. But Prisma then there was a gap. Nothing was launched for the longest time. Prisma was launched last year. NMAC will be launched. That's a German instrument. I'm part of the NASA Surface Biology and Geology Study Group, and that will be launched in 2027. I'm also launching my own hyperspectral imager, which is a 6U CubeSat, which is this thing. We're going to launch that in about a year and a half. In short, in the future, we won't need to be limited by the dual band technique because we will have lots of imaging spectrometers in space, and we will have lots of sensors, which means we will have imaging spectrometer data from more locations on Earth far more often than we ever had in the past. So I'll finish there and we can take some questions.
Okay, wonderful. A few questions that have come to me are people are requesting suggestions for particular papers or articles they might read to get a little bit more information about these methods.
Okay, I'll put a reading list together of a page of references, and I'll email that to you, Ryan.
Okay, sounds great, and I can share that out.
Yeah, it's like I say, if you look at the progression through time, I'll send you a paper from I'll send you Dozier's paper. I'll send you Rothery's paper. I'll send you a couple of Oppenheimer papers, Andy papers. You know, my papers, not because I'm an egotist and I'm going to send you my papers, but if you look at the reference lists, you'll see a whole bunch of other papers in there as well. Yeah.
Fantastic. I was just curious about these sort of new generation of hyperspectral thermal satellites. I mean, I'm much more familiar with visible near infrared hyperspectral. And I guess I would imagine there's all kinds of additional or different complications with a hyperspectral thermal kind of instrument. I was wondering if you could just speak about that a little bit.
So if it's in the thermal infrared, thermal infrared data will be useful for volcanologists for volcanic gas retrievals, volcanic ash retrievals, and then also retrieval of lava, retrieval of mineralogical work, and then low temperature geothermal anomalies. You wouldn't use the long wave infrared to study active lavas because, as I showed in some of those earlier slides, you get much more separation in the midwave and the short wave. Right. So if we just look at that set of curves that I showed at the end of part 1, if you just look at there's a log scale of radiance on the left-hand side, and you can just show to yourself, if something's really hot, you get 3 orders of magnitude separation in the short wave and the mid wave, and you get like 1 order of magnitude separation in the long wave. Yes. So you wouldn't use the long wave to study hot stuff. You'd use the short wave or the mid wave.
And towards that end, there's another question, but this is something I was thinking about. Typically, you're using nighttime images or daytime, or it doesn't matter too much?
Okay, can I show you I'll reshare my screen and I'll just talk through an example about that. Let's find it. Oh, I can just do it from here instead of being stupid. And okay, you can still see that, right?
Yes, I can see the yellow area curve. Yes.
Oh, can you see? Oh no, you can't see it. Hang on a sec. It's this one. You see that? The curve with the 3 bars on it and the loads and loads of curves?
Yes, now we do.
Right, okay. So nighttime versus daytime. If you're working in the thermal infrared part of the spectrum, then the Earth doesn't reflect any light. These are reflected light curves, right? This is top of the atmosphere solar irradiance multiplied by 0.05 for a basalt and 0.1 for a dacite, right? So if you're looking in the thermal infrared and you're trying to work out a temperature, the Earth isn't reflecting any light here, so you don't have to correct for reflected light. As the person who asked the question last time, you do have to correct for solar heating, right? Because if you shine light on this, it will get warm and these curves will move in that direction. So if you care about the volcanic component of the radiance, you should correct for solar heating, but not reflection. Let's take this pixel here. So at night, if I look at 1.6 microns, I measure like 30 watts per meter squared per steradian per micron from this lava flow, which is great. I've got tons of signal. The surrounding pixels or the land at ambient temperature isn't radiating any light at all because it's too cool. During the day, if it's daysight, say this is an active lava dome at Guatemala. As soon as I turn the sunlight on, the satellite measures, or there's about 25 watts per meter squared radiated by the lava, but about 5 reflected by the lava. Sorry, about 15 reflected by the lava, right? Where this gray curve and this red curve fall at the same wavelength. You see that?
Yes.
So the problem there is I have my signal is 30, and I don't care about the reflected light, but that's 15. So my noise or my contamination is half of my signal. And that's hard to do science, right?
So to take advantage of these, of the hyperspectral for getting at temperature retrieval, you really want to work at nighttime imagery.
You want to work at night because at night the sun turns off and then I have no contamination. right?
Yes.
By day, I've got to correct for solar reflected light, and it's a bad place to do science if the thing you're correcting is half of your signal.
Yes.
Right? Because
100%.
if you're 50% out on your correction, then suddenly your signal to noise ratio becomes 1.
Very good.
Which is
We
an
had
even worse place to do science.
sort of a big picture question. How do you see the future developments in volcanology when we have all these sensors available?
Well, a lot more people will be able to look at a lot more volcanoes and do a lot more exciting stuff. So, you know, when I was doing my PhD, I had 5 Landsat scenes. At the time, a Landsat scene cost $3,000. The only reason I had them was because I was working on a collaborative project with Dave Pieri at the Jet Propulsion Lab, and he had a load of money and he could afford to buy these things. I mean, I was doing my PhD in England. So I had 5 scenes, and if I hadn't been working with Dave, I wouldn't have had any scenes. And that was true for a long time. I mean, Landsat is free now, but it only became free 10 years ago. Aster has only become free in the last few years since the Japanese government decided they were going to make it free. So in the future, Europe and the US, NASA have a commitment to making all of these data sets free for everybody to use. They also have a commitment to making this data available in real time. So, you know, I used to have to order this data on tape and get it and load it up and drag it in. And I had to use a Sun workstation, which was, you know, wildly expensive, which meant, you know, there was a high bar for entry. You could, you know, a lot of people couldn't use it because they couldn't afford the computers, they couldn't afford the software, they couldn't get the data. Whereas with all this data being available for free, with low latency, i.e. you get it within hours of the spacecraft going overhead, and you can analyze it on a PC using Python scripts, something like that. Basically everybody, there's very little barrier to entry for lots and lots of grad students and students to really have at this data and squeeze every drop they can out of it. Now, in terms of the sensors, you know, it used to be, these things used to cost $1 billion and they were launched once every 20 years, right? Landsat, Aster. I mean, Aster is still the state-of-the-art long-wave infrared imaging sensor on orbit, and it's 21 years old in December. But with the reduction in launch costs, CubeSat, small satellites, we should see lots more sensors requiring lots more data that we can use for volcanological studies.
Okay, very good. We have another question here asking about other fields where the thermal unmixing method could work other than the field of volcanology.
So wildfires, you know, wildfires are a little simpler because there you generally do have 2 components at the pixel scale, right? If you know, with a lava flow, you have fresh lava, and then as soon as it's exposed to the atmosphere, it just cools to ambient. And as it cools between those 2 temperatures, it occupies every temperature in between, right? So, you know, unmixing the temperature is what I showed on you know, one of those charts. It's basically you have a continuum. With a wildfire, the temperature at which the fire burns is proportional to the energy which is released. And the energy which is released is the residual between the breaking and formation of bonds in the combustion reaction. So really, wildfires burn at a single temperature, right? When the fire goes, the ground is smoldering and it quickly cools back to an ambient temperature. So, you know, the dual band approach is more relevant for wildfires than it is for active volcanoes. So you can apply this technique there. Dozier, when he initially developed it, he was trying to work out the temperature of gas flares at oil wells. So he did it for that. We worked out about 10 years ago, I was working on a project about industrial applications, and we could correlate the energy radiated from oil wells in Iraq with the amount of oil production in millions of barrels per day. You can also do it for coal fires. You know, Anupma Prakash has papers in IJRS which use this method for coal fires.
Okay, very good. Let's see, there's a question here. What is the possibility of getting a good thermal hyperspectral imager in the future? May it be spaceborne or airborne, and the spatial resolution on par with current Vernier-Sweer resolution?
So this, you know, so the spatial resolution is a hard one, right? Diffraction limits you. Now this, what am I doing? Can you still see this last slide? This one with Prisma and Nmap?
No, we still see all the colored curve.
Okay, so, I've just worked out how to do this. I think. Okay, you see it now? Prisma, HiTi, Nmap.
Yes, now we do.
Yeah. So, you know, this thing here, so we're launching this in a couple of years. It's a cube satellite. It's 30 by 20 by 10. You know, it's diffraction limits you. You will always be diffraction limited in terms of the spatial resolution in the thermal infrared compared to the long wave, compared to the V-near and the short wave infrared. The spatial resolution of this is going to be about 60 meters on the ground. Now, we could have a larger optic if we had a larger satellite. There are issues with the thermal infrared in that you have to cool the detectors to various temperatures. I mean, the Landsat TIRS instrument uses things called QIPs, quantum well infrared photodetectors. They have to be cooled to 40 Kelvin. So the cooler works just like your freezer or your refrigerator at home. To cool really cold, you have to have a pretty big engine that's cooling you down to those temperatures, which increases the power consumption on the spacecraft, which increases the batteries, the solar panels, the thermal control problem. Equivalent spatial resolution in the thermal to the VNet is really, really hard to do, especially if you have lots of bands. Okay, because if you just work out signal to noise, as you divide the long wave spectrum, the long wave region into narrow bands, you decrease the signal to noise in proportion to the number of bands. So, you know, the new architecture for SBG, which was announced yesterday, at the moment, the architecture they're proposing is 2 free-flying spacecraft, a V-near spectrometer, which will have a spatial resolution of 30 meters, and then a multispectral thermal infrared mid-wave scanner, which will have a spatial resolution of 60 meters. So the state of the art for the long wave is still 60 meters. You know, unless you're some kind of spy and you don't care about spectral data, you just want to get a thermal image, then you can bin the signal in the thermal bands. You can get the signal back up, which means you can make the pixels smaller, but you'll never dodge the diffraction problem, which is how much the light spreads when you try and focus it on a detector element.
Okay, let's see here. Looks like one additional question. Can we use this technology to detect the movement of active faults before an earthquake?
The movement of faults, well, you know, this doesn't, not the movement of faults. You should Google. So there's you can Google a guy called Friedemann Freund. He used to work at the SETI Institute. I don't know if he still does, but he had an explanation for why there should be a thermal signature on the Earth's surface prior to an earthquake. And I did not understand his mechanism, but it was something like a non-temperature dependent long wave emission that was a result of the stressing of the rocks prior to the earthquake taking place. I didn't understand it. It hasn't been widely published, but if you Google Friedemann Freund, SETI, you should be able to find some conference abstracts or something like that that he might be able to shed some light on that. I know there are some papers that came out saying they detected thermal anomalies prior to large earthquakes, but I remember a guy called Matt Blackett, who was at King's College at the time with Martin Worcester. They did a rigorous statistical analysis of the same time series, and they concluded that there was no thermal anomaly associated with that earthquake. I think it was a large earthquake in India, in China. So if you Google Matt Blackett, he's now at Coventry University, you'll find his paper, which will contain a load of other papers on the subject of thermal precursors to large earthquakes.
Okay, oh, fascinating. Another question here. How do you see the use of VIRS data, VIIRS data in this domain?
So VIRS is the follow-on to MODIS. So VIRS will be what MODIS is now. So I was on the MODIS team. I'm now on the VIRS team. So Terra enters its, Terra will be breathing its last breaths from next year. They start deorbit. It starts coming off WRS next year. Aqua starts coming off WRS the year after that. By 2026, Terra and Aqua Modus will be turned off. VIIRS, the US is kind of dedicated to launching VIIRS instruments through the year 2031. You know, it's going to become the operational sensor that will replace MODIS. It's operated by NOAA, not NASA, which presents some issues, but VIIRS is kind of like a better version of MODIS. You know, it has all the same spectral characteristics pretty much. The spatial resolution is slightly better. It doesn't have the bow tie effect because they spent an enormous amount of money making sure that didn't happen. VIIRS can be used in exactly the same way as MODIS, as I'll describe in the next presentation.
Okay, great. I think that's all the questions for now.
Okay, so should we move on to the next
Sure thing.
presentation? Yeah. Sorry, I'm trying to work out how to do this. Still. Okay.
Well, actually, there was a request for a 5-minute break, if you think there's
Sure.
time for that.
Yeah, why not?
Okay, let's do that. So everybody, let's take a 5-minute break, and we'll be back, maybe a 7-minute break. So about 20 after the hour, we can start again.
Do you see my title slide, or do I need to share again?
I see, yes, thermal remote sensing of volcanoes with a beautiful photo to the side. Your title slide here, yes.
Topics related to low spatial but high temporal.
Yes.
Yeah, okay, great.
Okay, great.